Today, prepare to be dazzled by the remarkable discoveries of the James Webb Space Telescope. We always knew it would unveil intriguing secrets, especially about the universe's enigmatic early days. Imagine galaxies appearing brighter and more orderly than expected, defying the short time they had to evolve. But hold on to your cosmic hats, because the real plot twist is a whole new kind of star, one fueled by dark matter, radiating brilliance comparable to an entire galaxy. And guess what? This cosmic revelation might just crack the code of those perplexing giant galaxies. Welcome to SpaceVerse, your cosmic gateway to the wonders of the universe. Join us on an exhilarating journey through the vast expanse of space as we unravel the mysteries of black holes, explore the latest breakthroughs in astrophysics, and take you on a visual odyssey of breathtaking celestial phenomena. Subscribe, buckle up, and let's embark on an interstellar adventure together. In April, Nature Astronomy spilled the cosmic beans with a paper detailing the sighting of 4 celestial wonders: Jade's GSZ 10-0 to Jade's GSZ 13-0, or simply Z10 to Z13. Not the most poetic names, but hey, space is vast, and we exhausted the cool name pool ages ago. Admittedly, these objects may seem like mere dots, but cut them some slack. They're too distant to be sharply resolved. Trust me, though. These dots are among the oldest and farthest things ever glimpsed. C13 and Z12 are currently holding silver and bronze in the most distant confirmed objects competition, with C11 not far behind in a respectable 5th place. Discovered during the JWST Advanced Deep Extragalactic Survey, aka JADES, these celestial gems are part of a mission to unravel the mysteries of the universe's inaugural galaxies. The magic of JWST lies in its infrared prowess, revealing stars whose ultraviolet and visible light energies have been stretched into the infrared by the expanding universe. Some of these celestial wonders are over 30 billion light-years away. They're light journeying to us for the majority of the universe's existence. Picture this. We're peering into the cosmos as it existed a mere 400 million years post-Big Bang, a mere 3% or less of its current age. And now buckle up, stargazers. It's a cosmic journey like no other. Judging by the luminosity of these formations, at first glance, they appear to be complete galaxies. However, these galaxies are colossal, boasting masses hundreds of millions of times that of the Sun. While such massive galaxies are prevalent in the contemporary universe, the unexpected twist is their existence in the early stages when they had minimal time to develop. The enigma surrounding the substantial early galaxies unearthed by JWST has sparked considerable concern and even ventured into some rather unconventional speculations. Nonetheless, let's entertain the notion that we might be witnessing something truly extraordinary. Consider that we are gazing into the cosmic dark ages, a period when the pristine hydrogen born in the Big Bang obscured our view across a significant portion of the electromagnetic spectrum. It's a time when this same pristine hydrogen could give rise to stars thousands of times more massive than those formed today. Who knows what other phenomena might lurk at the fringes of our cosmic map? Maybe we're venturing into uncharted territories, perhaps encountering celestial dragons or even dark stars. This intriguing possibility is proposed in a recent publication in the Proceedings of the National Academy of Sciences, suggesting that 3 out of these 4 entities might be fueled by dark matter. The concept of dark stars was initially introduced by Catherine Fries and collaborators in 2007, but this marks the first instance of identifying potential candidates for these celestial objects. It's worth noting that the term dark star was first coined by John Mitchell in 1783 to describe an early version of a black hole. However, these novel dark stars are not the same. They aren't dark at all. In fact, they shine brilliantly. The perplexing question arises: how can dark matter, which is supposedly devoid of any interaction with light, generate such luminosity? Before we embark on the creation of our dark star, we must pinpoint a specific type of dark matter. For instance, the scenario doesn't align if dark matter consists of miniature black holes or failed stars. It necessitates a new, undiscovered particle, and even then, this particle must adhere to certain principles to give rise to a dark star. Initially, the primary stipulation for any dark matter candidate is its minimal self-interaction capability. This implies that individual dark matter particles cannot readily deflect off one another unless they come into extremely close proximity. This property ensures that dark matter can resist collapsing too easily under its gravitational influence, a crucial factor in explaining its existence as an expansive cloud-like structure enveloping nearly all galaxies. In contrast, particles within a gas cloud possess strong mutual interactions, inducing an internal friction that depletes kinetic energy, allowing the cloud to contract and give rise to stars. However, with minimal self-interaction, dark matter maintains its diffuse expansive state. An emphatically prohibited type of robust interaction is the electromagnetic interaction. Dark matter cannot emit or absorb photons, a requirement for preserving its dark nature. The second criterion for the formation of dark stars mandates that while the dark matter particle avoids strong self-interaction, it must exhibit some degree of weak self-interaction. This interaction strength must be finely tuned so that when the dark matter cloud is extensive, the particles experience almost negligible interaction due to their considerable separation. However, when circumstances bring these dark matter particles into close proximity, the weak self-interaction triggers the collapse of the dark matter cloud akin to a gas cloud, but under specific and extreme conditions. Crucially, this interaction also facilitates the annihilation of dark matter, constituting the final prerequisite. Delving into the cosmic mysteries surrounding the birth of dark stars takes us on a journey into the enigmatic realm of dark matter and its intriguing properties. For the cosmic spectacle of dark stars to unfold, the dark matter particles involved must possess a unique capability: the power to annihilate each other. This cosmic dance of annihilation could manifest in two distinct ways. First, the dark matter particle might be inherently its own antiparticle, paving the way for self-annihilation when two of these particles come into close proximity. This intriguing hypothesis takes center stage in the recent paper, suggesting a cosmic waltz of dark matter particles within their enigmatic realm. Alternatively, the annihilation mechanism could come to life if antimatter makes a cameo, appearing in particle-antiparticle pairs. The crucial element here is that the cosmic spectacle of annihilation occurs when these mysterious particles draw near to one another, setting the stage for the birth of dark stars and adding a cosmic twist to the narrative of the universe's evolution. Now, armed with a knowledge of the kind of dark matter required for this cosmic ballet, let's entertain the notion that this specific variety of dark matter does indeed populate the vast expanse of the cosmos. This assumption, while speculative, is not without merit. Consider prevalent dark matter candidates like weakly interacting massive particles, WIMPs, which, intriguingly, align with the criteria necessary for the cosmic symphony of self-annihilation to take place. These hypothetical particles, if they exist, hold the potential to be the cosmic architects orchestrating the birth of dark stars, adding an element of cosmic intrigue to our understanding of the universe's hidden and mysterious components. Now, embarking on our cosmic venture, we immerse the early universe in a rich tapestry of dark matter, saturating space with a substantial quantity of this mysterious substance intricately woven throughout the cosmic fabric. To add a nuanced touch to this cosmic canvas, we introduce a cosmic cocktail of hydrogen and helium, constituting approximately a fifth of the dark matter's pervasive presence. As we weave the cosmic threads, we introduce subtle variations in the density of all matter, creating cosmic tapestries with regions of higher density that weave the intricate patterns of the universe's inaugural structures. In this cosmic tapestry, the architects of the first massive stars emerge as mini-halos, cosmic nurseries with masses ranging from millions to hundreds of millions of times that of our radiant sun. Herein lies the cosmic challenge, particularly for the dark matter component, which is characterized by its weak interaction and faces hurdles in collapsing. However, amidst this cosmic dance, gravitational forces come into play, sculpting the destiny of the universe. The gas within these mini-halos responds to the cosmic choreography, gravitating toward the gravitational wells formed by regions of higher density. As this cosmic ballet unfolds, a pivotal moment awaits, a celestial crescendo poised on the precipice of star formation. The gravitational pull exerted by the dense regions triggers the gas within the mini-halos to cascade toward the center, converging in a cosmic dance that holds the promise of igniting the first sparks of stellar birth. The outcome remains contingent upon the scale and size of these cosmic cradles, these mini-halos, as they stand as cosmic incubators, potentially giving rise to the luminous beacons that will illuminate the cosmic expanse. Thus, our venture into the early universe involves orchestrating a symphony of cosmic elements, where dark matter, hydrogen, and helium converge to initiate the cosmic narrative, unfolding with the grandeur of the universe's inaugural structures. Also, we know that dark matter can be significantly influenced by the gravitational pull of ordinary matter. This dynamic comes into play in our scenario. The increasing density of gas at the halo's center would draw some of the dark matter inward. Within the central ball of gas, the density of dark matter would escalate to levels much higher than what we observe in the contemporary universe. This marks the birthplace of our dark star. The dark matter content within the star is relatively modest, constituting only a fraction of a percent of the gas's mass. However, its density is on the order of trillions of times higher than the typical dark matter density in a galaxy. This elevated concentration enables the dark matter particles to interact, leading to a crucial outcome: annihilation. This process releases a substantial amount of energy, primarily in the form of rapidly moving decay products. The resultant energy release heats the surrounding gas, preventing further contraction. Consequently, the gas ball fails to attain the necessary density to form a conventional star. Nevertheless, the dark matter annihilation generates significantly more energy than a standard star could ever produce. Our nascent dark star initiates as an inflated sphere a few times Earth's orbital radius and several times the Sun's mass. However, it undergoes expansion, drawing in more gas and dark matter from the affluent surroundings of the youthful universe. Its size grows multiple times, potentially reaching dimensions comparable to Saturn's orbit, or even expanding to millions of times the Sun's mass. At this scale, it radiates billions of times brighter than the Sun, brilliant enough for observation by JWST at the extremities of the universe. Now let's contemplate the fate of these hypothetical dark stars. Over time, the ongoing annihilation of dark matter would diminish the support for the gas cloud, hindering its collapse. Alternatively, a dark star might replenish its fuel by attracting dark matter from the surrounding halo. Regardless, when its life cycle concludes, whether spanning millions or billions of years, once the gas is no longer sustained, it would likely undergo rapid collapse, potentially evolving into a black hole. This aspect of the hypothesis is intriguing, offering a plausible mechanism for the swift growth of giant black holes observed in the centers of most galaxies. Dark stars could potentially serve as their originators, providing the seed black holes with masses equivalent to 1 million suns, which could then evolve into the billion solar mass behemoths observed in the earliest quasars emanating from the early universe. Are dark stars destined to remain in the realm of unverifiable speculation, immune to confirmation or dismissal? Thankfully, no. There are discernible observations that could effectively differentiate a dark star from a massive early galaxy. The key lies in analyzing the characteristic wavelengths of light absorbed or emitted by the gas within these entities. When we examine the light of a star through a process called spectroscopy, which involves splitting it into various wavelengths, we observe distinct sections missing at specific wavelengths. These are absorption lines resulting from the absorption of intense light deep within the star at precise wavelengths by surface-level atoms. Conversely, the spectrum of a galaxy typically exhibits emission lines indicating light emitted by cold interstellar gas illuminated by the adjacent starlight, producing the vibrant colors often seen in images of nebulae. If we acquire high-quality spectra of these objects, the presence of specific emission lines suggests a galaxy. Conversely, if there are no emission lines but we observe absorption lines, it would imply a solitary star. Given the extraordinary luminosity, a dark star emerges as a compelling contender for an explanation. While the possibility exists for a combination, a small galaxy housing a dark star at its core, analyzing the spectra should help distinguish such cases. Admittedly, these distant formations might simply be galaxies, albeit exceptionally unusual ones. For a comprehensive exploration of these purportedly massive galaxies and a critical examination of some of the associated hype, Dr. Becky's episodes on the subject provide an illuminating perspective. So, are we dealing with dark stars or galaxies? Galaxies appear more plausible primarily because we have tangible evidence of their existence, whereas dark stars remain speculative. Nevertheless, this scenario presents an exhilarating opportunity. We find ourselves at the intersection of a novel and peculiar observation, armed with clear methodologies to gain deeper insights. Whether these enigmatic entities turn out to be dark stars or galaxies, our exploration promises to unravel more about that mysterious epoch when the very first stars, be they dark or luminous, lit up the cosmos at the inception of space-time. And that's it, as we reach the end of our cosmic exploration journey. Thank you for joining us in the SpaceVerse. If you enjoyed this interstellar adventure, don't forget to like, share, and subscribe to stay updated on the latest mysteries of the universe. Keep the conversation going in the comments below. Tell us what cosmic wonders you'd like us to delve into next. Until our next cosmic rendezvous, keep looking up